All right. Now, getting this going again. Share. Were there any other questions about the homework before we move on? No? Does all of this make sense to everyone?
Yes.
Yes? Awesome. All right. In that case, chugging along, looking at week 4, we started off last class, or we ended last class talking about this idea of secant lines and of tangent lines. A secant line, I said, is a line that cuts through your graph in 2 points, or it shares 2 points in common with your function, is another way to think of it. So let's say our function looks something like this. We recognize that each of the points x, y represents an x value and the corresponding y value when you put that x through our function, right? You can write it like that. And in that way, if we have a line that goes through 2 points, let's say let's actually put a slightly different than what I had drawn. That's what I wanted. Like that. Okay. So we've got this line that cuts through exactly 2 points of our function. This would be considered a secant line, right? We can generally describe secant lines as some initial x value and compare it to some change in that x value. So if we have a set delta x or a set x, we could rewrite our points accordingly. What I mean to say is we can either fix x or we can fix delta x. For the sake of what we're going to be doing, let's fix x. Now we're going to go some delta x away. Draw this so that the point that's actually on the graph. Over here, our functional value is going to be f of a plus delta x. And we can connect these 2 points with a secant line. Let me choose red. Now we know the secant line. Let me label this as our function f of x. This is going to be our secant line, L of x. And we know L of x can be rewritten, or can be written in the form mx plus b, right? M here is going to be f of a plus delta x minus f of a, no mistake, f of a divided by a plus delta x minus a, which is just equal to f of a plus delta x minus f of a divided by delta x. And if we want to go through the hurdle of actually finding out what this equation is, we would use slope-intercept form. Point-slope form. And we would work it back to this, right? Now the question is, what is the C value? The C value can either be f of a or f of a plus delta x. But because it can be either one, I just decided to go ahead and write it as C. So we can be like, all right, we're not choosing one over the other. But when we get to writing out the slope or the slope-intercept form, we know to start off with one of those two, right? We can either, like I said, choose C to be either A or A plus delta X. Right? From here, we can work it back to slope-intercept form. Okay. So we can find the equation of this line if we so choose. In fact, we can find the equation of any line that goes through f of a just by changing delta x, right? So we can choose to let delta x be whatever we want it to be. We can get every line that goes through f of a using this set. Everybody cool with that? Now the question becomes, like I said in last class, what happens when you let delta x go to 0? What happens then? Well, letting delta x go to 0, we notice first that we get closer and closer and closer until our 2 points share the same point, right? And our line is no longer a secant line. It doesn't go through 2 points, it only goes through exactly 1. This line is called a tangent line. It's a line that touches your function in one spot, and at that spot can be thought of as approximately parallel to your function. So to explain what I mean about it being approximately parallel, notice as we zoom in, our graph appears to flatten out, right? And the more we were to zoom in, if we could zoom in beyond this, it would appear flatter and flatter and flatter until it looked almost like a perfectly straight line. And that perfectly straight line that it would appear to be would be parallel to this tangent line. So that's why we can think of a tangent line as a line which touches a curve at exactly one spot or at a particular spot and appears to be parallel within a small neighborhood. What this word neighborhood means is for a small change in your x values. Does that make sense to everyone? Folks at home, does that make sense?
Yes.
Awesome. So before I go any further, I want to show y'all two examples. First, the difference between I've got to share screen, don't I? Wah, wah. Share screen. Okay. So the first graph is an example of a secant line, right? And if we fix our x value to be 1 and send that second point to it, we get this tangent line. Now, what this functionally looks like, don't save. What we can think of this functionally looking like is like this. Please let me zoom in. You're not gonna let me.
Can you do something in the top right hand corner of that window instead of 100%? You see that?
Yeah, good catch. Good catch. Dope. Thank you. All right, cool. Still sharing. Awesome. So what this functionally looks like, in this case, we start off with two different secant lines. And the reason why is because we can either add delta x or we can subtract delta x, right? And if we subtract it, we get the secant line that goes through a point over here. And if we add it, we get a secant line that goes through a point up here. Now, if we let that delta x get small and go to 0, what's happening is that our secant lines slowly approach this tangent line. Now, these tangent lines are important because, well, for a couple of different reasons, but one of the big reasons is we can think of these tangent lines for really small changes in x to be approximately equal to our function, right? So if we let h be a really small number, or at delta x, I'm going to erase this over here right now, just to show what I mean. let's say we have the function f of x is equal to, I don't know, x squared. That means, well, and let's choose our x value to be 1. If we were to find the equation for the secant lines that go through this point, let me draw that out on the board. Let me draw exactly what I'm trying to say, so that it's easier to see. All right, this is our function x squared. This is x is equal to 1. This is f of 1 is equal to 1. Now let's just concern ourselves with the secant line that goes through a point up top. Kind of like that. Everybody with me on this? Okay. This is going to be x is equal to 1 plus delta x. This is going to be f of 1 plus delta x. Now let's let delta x be really small. For now, let's let delta x be, say, 1/10. Seems like a good number, right? Then this line is going to have the slope f of 1 plus delta x minus f of 1 divided by delta x. Well, this is 11/10, that quantity squared, minus 1 squared divided by 1/10. This is going to come out to be 121 divided by 100 minus, let's rewrite this 1 as 100 over 100 divided by 1/10. So our slope here is going to be (21) divided by 100 divided by 1/10, or just 21 divided by 10, right? This slope is going to be 2.1. All right, so we have 2.1, and we know two different values. Let's go with the easier of the two. X is equal to 1, and our function at 1. Y minus f at 1 is equal to 2.1 times x minus 1. Everybody agree with me so far? All we're doing is trying to find the equation of our line. And what we're about to see is that after we get the equation of our line, for points really close to x, our line is going to be really close to our function value. Everybody cool with that? So, let's tighten this up. This is going to give us y minus 1 is equal to 2.1 times x minus 2.1. Adding 1 to both sides, y is equal to 2.1 x minus 1.1. Just for the sake of argument, put 1 in here. You put 1 in here, you're going to get 1 back out, right? 2.1 minus 1.1, it's going to be 1. And if you put any number close to x in here, you're going to get numbers close to our function at 1, right? Is everybody cool with this? And the smaller our delta x is, the closer these numbers will get. So if we chose, say, 1/100th, these numbers would cut out to be even closer, and even closer, and even closer, and even closer.
But never touching, right?
But never touching except at that one point.
So you just selected 1/10 at random?
Just to demonstrate that for really close values, or for really small values of x close to 1, right? Our secant lines will be close to our function. And as we choose smaller and smaller delta x's, our values will get closer and closer to our function. Does that make sense what I mean? And that's kind of what we see happening up here, right? First, we start off with secant lines that are way far apart. First, we start off with secant lines that are way far apart, and then they get closer and closer to our tangent line. But our tangent line is actually pretty close to our function for a hot minute, right? And that's the point of this. So this tangent, for small values, for small changes in x close to a, it's going to be damn close to your function. And it's only going to touch your function at one point. And at that one point, you can think of your function as having the same slope as your tangent line. Does all of this make sense? I'm throwing a lot all at once. So if we're going to zoom in on this idea of the tangent line. All right, so we got our tangent line. Now let's zoom in. Better. We're going to zoom in again. There. Our function would appear to get flatter and flatter and flatter, closer and closer and closer to this tangent line. If we could keep zooming in forever and ever and ever, right? So we can think of a basketball and zoom in on the surface of a basketball ball, right? It appears to be flat if you zoom in close enough. Or the Earth. We know the Earth is a sphere, but we experience it as being flat because the scale at which we exist is more like this compared to the actual size of the ball, right? Of the sphere. And in that same way, as you zoom in, it becomes harder and harder to distinguish between your tangent line and your function. So, in some sense, the slope of your tangent line at A, or the slope of your tangent line can be thought of as the slope of your function at A. Like I said, jiggle A a little bit, jiggle your X around A just a little bit. And it's really hard to distinguish the difference between these two. Everybody cool with this? Now, the slope of our tangent line, that's a little special. That has a couple special properties. Well, that is a special value, I should say. Bringing up these notes again. The slope of your tangent line is going to be the slope of your secant line as delta x goes to 0. We've already seen that. This is the limit definition of what's called the derivative. So, as one example of how we can apply this definition, let's say we want to find the tangent line to the function x squared at x is equal to -2. First thing we would do is find the slope, right? Well, the slope is equal to this as delta x goes to 0. So we take the limit as delta x goes to 0. Here we find the slope is -4. From here, if we wanted to find the equation of the tangent line, we would use point slope formula using just this one point and this slope. Is everybody cool with that? So what I'm saying is, we found through this the slope of the tangent line to the function x squared at the point -2, at x is equal to -2. All right, so we've got the slope. Now let's find the equation of that line. So we're going to use the point -2, 4. We know our slope is -4. So y minus 4 is equal to -4 times x minus -2. going to be y is equal to -4 times x, -4x. We can replace that with addition of 2, right? Minus -2 is the same as adding 2. So this gives us -8 plus that whole. Agreed? So the equation of our tangent line here is -4x minus 4. The entire process, from start to finish. First thing you do, find the equation of the tangent line. Determine what your function is. And what point you want that tangent line to be at. Solve n is equal to f of a plus delta x minus f of a. My mistake, let me write in the limit before I do anything else. The limit as delta x goes to 0 of f of a plus delta x minus f of a divided by delta x. And then finally, we're going to rewrite point slope form in slope intercept form. This is how you find the equation of the tangent line. Now, what we just did was we said, all right, they went ahead and solved part 2 for us. That is all this. All right, cool. So we have our xy, that's -2, 4, and we have our slope. The equation we were given was x squared. So we're going to find the tangent line, rather the line tangent to the function x squared when x is equal to -2. That's what we're finding up here with the board right now. Given that they solved for our slope, given that we knew our point, we put everything into point slope form, and then we solve for slope intercept form. Is everybody cool with this? Okay. Cool, awesome.
Okay, wait, I have one random question. You, it's probably just the order that you do it in for this side. You, looking at purple, y minus 4 equals -4. So you factored in the -4 first, and then you added over the 4?
Yeah, I just went ahead, multiplied everything out, right?
Okay, yeah,
Distributed that -4, and then added 4.
okay, so do
So-
that, distribute before you add from the other side. Because if I just, because I was thinking to just add over the 4, but that would just leave me at x plus 2.
Well, you could do that, right? The thing that would happen is, first you need to remember that this 4 is distributed to only these terms.
Okay,
So if you add 4, you still have to distribute this -4 all the way through.
okay,
That's why I did it here.
which
and
makes
then
sense,
added 4.
okay. Because I would
Makes
have
sense.
just added the 4 and then I'd be like, oh, look, it equals out, and then I'd be happy. But no, I can't do that.
Not quite yet.
Okay.
No, we have to distribute that
Distribute
-4, then
And
add
then, okay,
4.
no shortcuts, I guess. Okay.
Everybody cool? So finding the slope of a graph. Well, we know that this is in slope intercept form. So m here is going to be -2. So our slope of this graph should be -2, right? It's -2. Nothing insane here. But if we wanted to, we could find the slope of this graph using this limit definition that we just talked about. Because the tangent line to any of these points will be the tangent line to every point, right? Since this is just a straight line, if a line is tangent to our function here, it's going to be tangent to every point, right? And that's what they're doing here. Is they're just using the limit definition of the slope of the tangent line to find the slope of the tangent line to this function, but that tangent line is tangent to every point, so the slope of our function is -2. Does that make sense what I mean? Now we could generalize this further. Instead of saying A, we could just write in X, right? Substitute in X here, here, kind of here, and solve for this, right? And get a general solution if we wanted to. So imagine here, you're asked to find the slope of our graph, so of our function here, x squared plus 1, at 2 different points. Doing this thing over and over again would suck. So what if we could do it once? And then just plug in our x value. That'd be a lot better, right? Just get a general formula for our slope of our graph, no matter what the x value is. So what we're trying to find is the slope of our function. You're at -1, you're at 2. Again, the slope of our function at a point you thought of as the slope of our tangent line. They're analogous to one another. So when they talk about getting the slope of a graph, what they're really saying is find the slope of the tangent line. So here, what we're going to do is just substitute in x for each of these a values. I'm going to solve that up here on the board now. All right. So we want the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. Well, this is the limit as delta x goes to 0 of x plus delta x, that quantity squared, plus 1 minus x squared plus 1 divided by delta x. Okay, expanding this out, the limit as delta x goes to 0 of x plus delta x, that quantity squared, is going to be x squared plus 2x delta x plus delta x, that quantity squared, plus 1 minus x squared plus 1 all over delta x. Now notice, here we can drop our parentheses, right? And we can distribute this negative all the way through. To end up here. Everybody agree with me? So all I've done is said you can drop a parentheses, right? Dropping those parentheses, we're going to get the limit as delta x goes to 0 of x squared plus 2x delta x plus delta x, that quantity squared, plus 1 minus x squared minus 1 over x delta x. Well, hey, we've got a bunch of cancellations now. The 1's cancel. And the x squares cancel. So I guess I shouldn't say a bunch, but we've got some cancellations. Dope. So what this means then, is this is going to be the limit as delta x goes to 0 of 2x delta x plus delta x, that quantity squared, divided by delta x. Well, hey, I can factor out a delta x, can I? So let's do that. I'm going to come over here and factor out that delta x. This is the limit. As delta x goes to 0 of delta x times the quantity 2x plus delta x divided by delta x. Hey, another cancellation just showed up. So let's take care of it. So what we're left with now is the limit as delta x goes to 0 of 2x plus delta x. Well, hey, that's just 2x. So for any x value, the slope of this particular function can be found using this equation, just 2x. So if we want to find the slope at the point -1, 2, just throw -1 in there. If you want to find the slope at 2, 5, just throw 2 in there. So if you want to find the slope here, this slope should be -2. If you want to find the slope here, this slope should be 4. Now comparing really quickly with what the book's got going on, we start off with the general equation, and they don't apply the limit until much later, way down here, right? I say go ahead and just apply the limit, work out the algebra. I think it saves a mental step, I feel like. To me, this feels like less work than breaking it up into 2 parts. It's just my personal preference. But notice it doesn't really change anything, right? Because when we simplify, we're still going to get to 2x plus delta x, whenever delta x is not equal to 0, right? Because way up top, we couldn't have delta x equal to 0. But otherwise, these two things are the same. Now, when we apply the limit and let delta x go to 0, she's going to give us 2x. Exactly what we just found. So if you want the slope of any tangent line to this function, this is the general equation that defines it. So now we can come over here and say, all right, cool. Whatever our values of a's are, just plug those into here to find n. Follow the rest of the steps, right? Now this thing is so commonly used. It's so important, and it shows up literally everywhere in mathematics. So much so until you've given it its own name. It's called the derivative. This is the limit definition of the derivative. And we denote the derivative in a bunch of different ways. So the limit is delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. This thing is called the derivative. We oftentimes will denote it as f prime of x. We may also denote it using a bunch of other notation. df of dx. We may use dy dx. Every now and then in engineering stuff, you'll see something like that. What other notations am I forgetting here? A bunch, but this is generally what you might see. We could also write this as the f of x dx and dx f of x. So there's a bunch of different ways of denoting this. Just in case we come across any of these and you're like, why? It all means the same thing. Unfortunately, two different people at the same time, air quotes, because Newton didn't do it first, Leibniz did. Two different people at the same time derived calculus and used different notations. We have Newton's notation and Leibniz's notation. Leibniz beat Newton to the punch. Fight me. I dare you. Physicists, you are wrong. But having said that, I think this is a natural point to stop and take a break. So why don't we take a 10-minute break, come back, pick up where we left off.